All right, let's dive deep into electromagnetism. And look, I know this can seem like just another subject in a textbook, but it's so much more than that. It's really the fundamental language of electrical engineering. It's the invisible architecture that literally powers our entire modern world.
And it all really starts with a pretty simple question. I mean, think about it. How does your phone send information through the air? How does your Wi-Fi router beam the internet to your laptop with no wires? The answer to all of that, well, it's woven into the very fabric of electricity and magnetism.
So, here's our game plan. We're going to start with the magic of wireless, then look at the 4 fundamental rules behind it. After that, we'll see how to create and catch waves, link it all back to simple wires and circuits, and finish up by looking at the true power of electromagnetism.
Okay, let's jump right in. First up, the magic of wireless. So, how do we send information through thin air? I know it can feel like magic, but I promise you it's pure, elegant physics.
The hero of this whole story is something called an electromagnetic wave. Now, the best way to think about it is like a ripple, but not a ripple in a pond, it's a ripple in space itself. And this disturbance is made of 2 parts that are just completely intertwined, an electric field and a magnetic field. They're basically dancing together as they travel. This wave is what's carrying the signal for your radio, your cell phone, your Wi-Fi, all of it.
And this image, it shows that dance perfectly. See the electric field oscillating up and down? And the magnetic field goes side to side. But here's the really cool part, the crucial part. They are perfectly in sync. They're always at right angles to each other, and they're both at right angles to the direction the whole thing is moving. It's this amazing self-propagating structure that lets the wave just race through the vacuum of space at the speed of light. It literally keeps itself going.
Okay, but why? Why do they behave like that? What's forcing them into this incredible, elegant dance? Well, that brings us to the 4 fundamental rules of the game. Believe it or not, this entire cosmic game is governed by just 4 equations. We call them Maxwell's equations. And please, don't let the math scare you. Think of them less as equations and more as the complete rulebook for all of classical electricity and magnetism. Seriously, everything we're talking about today, it all comes from these 4 simple-looking lines.
What's just so brilliant about these is how they create this perfect self-sustaining loop. Look at the first 2. Faraday's law says a changing magnetic field creates an electric field. Then Ampere's law says, hold on, I can do that too. A changing electric field creates a magnetic field. You see that? It's this beautiful back and forth, this give and take, that actually gives birth to the electromagnetic wave we just saw. And the other 2, Gauss's laws, they just add the details. They basically say electric fields come from charges, but magnetic fields always loop back on themselves. So you can't have a north pole without a south pole. No magnetic monopoles, as they say. The universe just doesn't allow it.
Okay, so we've got the rules that describe the waves. But how do we, actually make one on purpose? Well, it turns out the recipe is surprisingly simple. All you have to do is take an electric charge, say an electron, and just shake it, wiggle it back and forth. That's it. That acceleration is what gives birth to radiation. When you really get down to it, every radio station, every GPS satellite, even a simple light bulb, it's all just a machine designed to accelerate charges. And what's the simplest way to shake those charges? An antenna, specifically a dipole antenna. You can just think of it as a small piece of wire. We push an electric current back and forth along it, and that's our acceleration. That simple little act, which is totally governed by Maxwell's equations, is what creates those intertwined electric and magnetic fields that then shoot off away from the wire as a wave.
But here's the thing. The antenna doesn't just randomly spray that energy everywhere. No, it creates a very specific pattern. As you can see here, the radiation shoots out strongest from the sides, and it's weakest off the ends. This is where the real art of electrical engineering comes into play. Designing all these crazy, complex antenna shapes to focus that energy exactly where you want it to go.
All right, get ready for a real aha moment. We've been talking all about these big ideas, waves traveling through space. But it turns out, these exact same rules have a really surprising link to something every single electrical engineer learns on day 1, basic circuit theory. And here it is, the big reveal. Kirchhoff's laws, KVL and KCL, the bedrock of all circuit analysis, they aren't fundamental laws of nature. Get this, they're actually just simplified low-frequency approximations of Maxwell's equations. Kirchhoff's voltage law is basically a stripped-down version of Faraday's law, and Kirchhoff's current law, that comes from Ampere's law. Mind-blowing, right?
So why do we get away with this simplification?
Well, it's because basic circuit theory makes some really clever assumptions. It basically pretends that all the interesting stuff, all the magnetic and electric fields, are neatly contained inside the components, inside the inductors and capacitors. And at low frequencies, that works just fine. But as you ramp up the frequency, say in a modern computer processor or a 5G antenna, you can't ignore the waves anymore. That's when circuit theory starts to break down, and engineers have to go back to the source, Maxwell's equations, and start thinking in terms of waves again.
Okay, so this brings us to our final piece of the puzzle. These rules don't just describe invisible waves and simple circuits, they also describe real, tangible physical force.
The equation that does this is called the Lorentz Force Law, and it's basically the bridge connecting the invisible world of fields to the very real world of pushing and pulling. It tells you exactly how much force a charged particle feels when it moves through electric and magnetic fields. And think about this. This one single equation is the core principle behind every single electric motor and generator on the entire planet.
And believe me, these forces can be absolutely mind-bogglingly powerful. A great example is something called the pinch effect. Imagine you blast a massive amount of current through a thick wire. The little streams of current flowing side by side inside that wire actually attract each other. The magnetic field they create generates this incredible inward force that literally squeezes the wire. If the current is high enough, this force is so immense it can physically crush solid metal. It's a huge deal in things like fusion research.
And this is why all of this matters so much. When you stop and look around, you see it everywhere. The wireless signals connecting your phone, the radar guiding planes, the simple circuits in your kitchen appliances, the powerful motors in an EV, even the MRI machine at a hospital. It's all governed by this one beautiful, unified theory of electromagnetism.
So when you really think about it, it's pretty profound. The signal from your phone, the engine in an electric car, and the light from a star that's been traveling for billions of years. They are all just different expressions of the exact same four rules we looked at.
Which leaves us with one last really fascinating thought. James Clerk Maxwell figured all of this out and published these equations over 150 years ago. Since then, they've given us radio, television, the internet, technologies that completely changed the world. So the real question is, what else is hiding inside this timeless code, just waiting for us to figure out next?